1.3 billion years ago, in a galaxy far, far away, two black holes merged. As they violently spiraled into each other, they created traveling distortions in the fabric of space-time, gravitational waves. In the last tenth of a second, the energy released in these waves was 50 times greater than the energy being released by everything else in the observable universe combined.
It's like an awe-inspiring kind of energy.
After spreading out through the universe at the speed of light for over 1 billion years, the waves reached Earth, where they stretched and squeezed space such that two light beams traveling in perpendicular pipes were put slightly out of step, allowing humans to detect the existence of gravitational waves for the first time. That's a simple enough story to tell, but what I found out when I went to visit Professor Rana Adhikari at Caltech is that it hides the absurdity of just what was required to make that detection.
There's a lot of things about gravitational waves which are absurd.
That's it?
Yeah.
The main problem with detecting gravitational waves is that they're tiny. They stretch and squeeze space by just 1 part in 10 to the 21. That's the equivalent of measuring the distance between here and Alpha Centauri, and then trying to measure variations in that distance that are the width of a human hair. To detect such tiny wiggles, you have to measure over as large a distance as possible, which is why the arms of the interferometers are 4 kilometers.
And even with arms this long, gravitational waves vary the length of the arms by at most 10 to the minus 18 meters. So the detector has to be able to reliably measure distances just 1/10,000th the width of a proton. It's the tiniest measurement ever made. So how is it possible to measure that, considering all the other sources of vibrations and noise in the environment, like earthquakes, traffic, and electrical storms? Well, for one thing, the mirrors are the smoothest ever created. They weigh 40 kilograms or 90 pounds and are suspended by silica threads, just twice the thickness of a hair, to isolate them from their environment. And even then, the only way to be certain not to be tricked by environmental noise was to build 2 detectors far apart from each other in reasonably quiet locations. That allows you to distinguish between local noise, which would appear at only one site, and gravitational waves, which would pass through both sites almost simultaneously.
I'm in a building that contains a 1 to 100 scale of LIGO, the gravitational wave detector. The next challenge is the laser. Whoa.
Whoa. It's a lot of stuff.
It is a lot.
You need a laser that can provide one and exactly one wavelength.
You can imagine if your laser wavelength is changing and you're trying to use interference of light waves to make this measurement, it's never going to work because it's something like trying to measure this distance, but your ruler stick is constantly changing back and forth. You can't tell how many inches this is. All this equipment, at least 3/4 of it, all we're trying to do is make the laser more stable. And by the end of the day, what we've achieved is something which has a stability of 1 part in 10 to the 20. What does that mean? That's 100 billionth of a trillion. That's kind of what we end up with.
The best lasers for this purpose have a wavelength of 1064 nanometers. That's infrared light. But this presents a problem. How can you measure 10 to the minus 18 with 10 to the minus 6 wavelength of light?
Yes. I wish more people would ask this question.
It's great for this animation to show such a large shift in the wavelength, but the reality is, it's only 1/trillionth of a wavelength that the arms are shifting in length.
It seems obvious that you can measure half a wavelength because that'll cause the light to interfere with itself.
Yeah, but that's fully. That'll go from completely dark to completely bright.
So are you looking at like slightly darker and slightly brighter?
Yeah. And the limit here to how good we can measure this difference between dark and bright has to do with the fact that the light is discrete. It comes in discrete chunks, which are called photons.
The variation in the number of photons hitting the mirrors at any instant due to this quantum uncertainty is proportional to the square root of the total number of photons. What this means is the more photons you use, the smaller the uncertainty gets as a fraction of the total.
This is why the laser power in the arms is 1 megawatt. That is enough energy to power 1,000 homes in a light beam.
And a megawatt, boom. It won't even rip your head off. You just vaporized. It'll be just a smoking stump.
Even with a perfect laser and 1 megawatt of power, anything the light hits would interfere with it, even the air. So all the air in the arms of the detectors had to be eliminated. And it took 40 days to pump down to just a trillionth of atmospheric pressure. And the tubes were heated up to the temperature of an oven to expel any residual gases. They pumped out enough air to fill up 2.5 million footballs, making it the second largest vacuum in the world after the Large Hadron Collider. Now here's something most people don't think about, which is that gravitational waves stretch spacetime. So light traveling through that space should be stretched as well. If everything is stretching, how do you know anything is stretching?
How do you know anything is stretching? That's the conundrum. It doesn't make any sense. This whole thing is bogus. Shut it down. I would send the laser beam down this tube and then wait for it to come back, and then I would say, well, nothing happened because the space got stretched and the laser wavelength got stretched. It looks the same if it got stretched or not stretched. Exactly. It doesn't make any sense. Well, it's sort of a matter of timing is how it works. So the amount of time it takes for light to go down this tube and comes back is very short. However, the wave, the gravitational wave, when it comes through, it's doing this slow thing, like this noise I made, which is low. It's a slow stretching. It's only 100 times per second. And it's true, when the wave comes through, the light which is in there, it actually does get stretched. And then that part doesn't do the measurement for us. But now that the space has stretched, that laser light is like come and gone. It's out of the picture. We're constantly shooting the laser back into the system. So the new fresh light now goes through there and has to travel a bigger distance than the light before. And so by looking at how this interference changes with time and keeping the laser wavelength from the laser itself fixed, we're able to do the measurement.
So what was needed to detect gravitational waves? Well, a megawatt of laser power to minimize shot noise of exactly 1 wavelength, because we're trying to measure just a trillionth of that wavelength. Continually inserted to replace older light that's been stretched and squished in the world's second largest vacuum chamber at just a trillionth of atmospheric pressure, hitting the smoothest mirrors ever created suspended by silica threads at 2 distant sites to eliminate noise, with 4-kilometer-long arms to increase the magnitude of gravitational waves to just 1,000th of the width of a proton.
You know, what we already do daily in here is what I would have said is impossible if you'd asked me about it 20 years ago.
One of the things that was most interesting for me to learn was what is limiting the sensitivity of the detectors today. And it turns out it is quantum mechanics, and essentially you can think of it like a Heisenberg uncertainty principle. We've got 2 things, and together their uncertainty has to be bigger than a certain value.
Luckily, for us, we're only trying to measure 1 thing here. We're not trying to measure 2 things at the same time. All we want to know is how much more did this arm get stretched from that arm? And that's the key point, which people did not understand until recently. The way to build these systems is such that they're extremely good in measuring 1 thing, and that all of the uncertainty which comes from quantum mechanics is completely crammed into this other thing that we don't care about.
I feel like we're getting down to these levels of nature where it seems like nature doesn't want you to go any further. But through our ingenuity, we're figuring out ways to engineer quantum noise. I think that's such a remarkable concept, and I look forward to the results that it's going to bring.
I think the next logical step is to go from 2 signals to detecting all the black holes in the universe all of the time. It's not like an alien civilization level of technology. It's just, we have to do a lot better than what we're doing now, but I see it sort of within our grasp.